start it right now. Okay. Today I will be talking about the pre-calculus. It's actually a preparation of the calculus, and the calculus that we have been discussed about is actually the implications of the polynomial functions as well as the rational functions. The implications of the polynomial and as well as the rational functions is actually how we're going to understand this particular chapter. And then we're going to learn about applications of it, because we have to know the reason why we learn about this particular topic. The next is that why? What is the reason why we learn about the polynomial as well as the rational functions? Any knowledges we're going to learn about that, we need to know the reason why we're going to learn it. How we're going to apply this knowledge to our really daily life, as well as how we're going to apply the knowledges into our work. Then, the reason why for learning this particular knowledge is because of, first of all, is the architecture engineering. If you want to specialize your degree in engineering, or finance, or research, or physics, or light intensity, or even design, architecture design, you have to know about the polynomial functions as well as the rational functions. If you're comfortable with that particular mathematical equations, of course, it's quite easy and convenient for you to apply the certain knowledges into the polynomial, into the real applications. For example, if you know about the rational functions, it's quite efficient for you to actually tackle the question about populations. Later we'll show about that. Okay? And that is the particular sectors you will go further. If you go to university or study of a certain subject, you need the basic like mathematics to learn about that future subjects. For example, you will specialize in engineering or finance or in business or social science. You have to know about that particular functions. Then we have actually learned about linear quadratic. We learned already. And I'm going to focus on is that the polynomial function with higher degree with modeling. How we're going to model the different scenarios using the polynomial functions. The next is that the real zeros of polynomial function. Actually, we have discussed about already for the previous classes is the roots of the polynomial functions. Then is the complex zeros of the polynomial functions. Now let's do a quick review for our definitions of the polynomial functions. First of all, is that if we have the polynomial functions, well, we'll discuss about fx equals to an xn plus a n minus 1 x to the power of n minus 1 all the way to n naught. We have a poly meaning that many different terms to illustrate that particular functions. We have n as the highest degree of the first term of the polynomial functions. Then we also have an as leading coefficients. We call all this actually is the coefficients of the polynomial functions. Then we call the first term as the leading coefficients. Of course, there are some special cases like 0 is also a polynomial function, because 0 is just x to the power of 0. A 0 function is also a polynomial function with no degree and no coefficients. Okay? Then we move on to the expressions of the polynomial functions and some of the examples. We have that standard form of the polynomial functions. Then we understand that actually the way that we name the polynomial functions, actually we have the leading coefficients as well as the degree. Well, we call this first term is the leading term. So I use this one, an xn is the leading term. Well, the an is the leading coefficient. Okay? So anytime when we talk about that, we're talking about the leading terms of the polynomial functions, and the many terms to illustrate it consists of many, so we call it the polynomial functions. Then the next we're going to study the graph of the polynomial function, which is the graphical modeling of the polynomial functions. Let's look into different type of the graph that we have been discussed about previously. Is that this graph is continuous, right? And this graph is actually have the jumping discontinuities according to our textbook. Well, this graph is actually not the smooth and it is not the polynomial functions. Well, when we study about the functions, we understand the graph is, we call it the simulation processes all the way to the graph. To further better understanding the property of the functions, we will have that the polynomial function, we will be notice that this one always continuous and smooth, and also they have the wrong terms. We have learned about that. This particular wrong term, we call it extrema, right? And then we have so many terms and graphs and points. Finally, we will find out how are we going to do the simulations of the polynomial functions and be able to understand the graphical modeling of the polynomial functions. We call it the simulation parts. So to make it a summary is that, first of all, we want to find out extremas, zeros, and behaviors, and then we sketch the graphics. So that is the basic property that processes, systematic processes, we're going to simulate it or graph these polynomial functions. Well, A is the zero of the fx. Well, A is also a solution of fx if fx equals 0, and A minus 1 is a factor of the polynomial functions. In this term, you have to understand about the standard form versus the factorizations. Factorization form of actually the polynomial functions is actually in terms of fx equals to different type of the factors. So we call this term actually a factors, right? So you factor A times in factor B all the way to here, we call this form is actually factorization form. Well, this form is actually the standard form. Then actually this term A0 is the zero of the polynomial functions. Then we have actually x minus A is a factor of the fx. So you have to understand that how are you going to transform the polynomial function into different type of the form. For example, how are you going to probably transform the standard form into factorization form? And if given a factorization form, how are you going to transform or translate it into the polynomial standard form? Then we have all the way back to the graphical modeling of the polynomial functions. If you look at the graph of the polynomial functions, interesting part is that they have the m behaviors. If you notice about the English term of the m behavior, is actually the behavior of the very end of this polynomial functions and very end of this polynomial functions, and actually the zeros of the extremas of the polynomial functions. So here, we actually introduce a mathematical way or tools to find out the end behaviors of the polynomial functions. We'll just take a notice that it's called limit. The way that we find out end behaviors of polynomial functions is actually we're taking the limit when x is very close to positive infinite of these functions, fx. Then we find the very end behaviors of this polynomial function. Just for example, this one is actually equals to positive infinite. Wherever we'll take a limit of when x is very close to negative infinite, fx, we have a negative infinite. So here is actually articulated that actually the polynomial function has the end behavior of positive infinite and negative infinite of the functions. We have learned about that, right? Then we come to the modeling, okay? Well, the zeros and extrema is just that the line that superimposes into the fx polynomial functions. Later we'll look into it by some examples. Then we learn about zero, we learn about rational zeros, right? The zeros of the rational zeros of polynomial functions. We learn about how we're going to find out rational zeros previously, right? It's x equals to p divided by q when we do a trial versus, right? We find out the trial of the polynomial functions. Then finally, p is actually related to the a naught, and q is actually related to an. Okay? A naught, an. Now, we have also learned about certain complex zeros and the factorization form of the polynomial functions. So here, linear factorizations is actually linear factorization is actually the different form I have been talking about, the differences. Then we learn about the factors of the polynomial function, which is the factor 1, factor b, 2, all the way to different factors. So we call it the factorizations of the polynomial functions. Then we learn about all degree of polynomial functions probably from our previous classes. Then now I want to introduce a very interesting part is that very, very unique parts of the polynomial functions that it is so-called, the new knowledge to us is rational functions. Why? Well, the reason why this one is quite interesting is that rational functions actually constructed in terms of different types of polynomial function. It is a division of the polynomial function. So I use P or P2 as two types of the polynomial functions. Of course, P2 cannot be 0. You can say it's long division. Previously we learned about that. So the long divisions of a polynomial functions is actually so-called the rational functions. Okay, make it more worse. Okay, rational functions. So we're going to learn about the graphical transformation of the rational, as well as the limits and the asymptotes of the polynomial the rational functions. Now let's take a look at the rational functions as a very, very typical way is that the reciprocal functions that we'll discuss about that is actually x over 1 over x. After a lot of the numerical modeling of the 1 over x, finally we find out an interesting part that the graphical modeling of a reciprocal function, which is also a rational function, 1 over x is actually looks like here. Okay? What is the reason why that we actually look at here? Now I'm going to using the mathematics to prove that. Why? What's the reason why the graphical modeling of the rational functions which is probably a typical one, is reciprocal functions. It looks like this way. Okay? So first of all, we're going to do a very interesting mathematical part, is that this is fx equals to 1 over x. X cannot be 0, right?
Yeah.
Now, right now the time is that we want to take a limit of 1 over x is actually, we take a limit when x is very close to positive infinite of 1 over x. That will be what happened is that, in this case, if we take x equals close to positive infinite, then we substitute the positive here, right?
Yeah.
Then this one will become
Smaller.
smaller and smaller, all the way close to
0.
0, right?
Yeah.
That is the one of the m behaviors of the rational function we want to study. The next is that we want to take limits that x is very close to negative, right? Negative infinite, but 1 over x. That will be close to, Harry? Close to 0. So now we come up with the graph of picture in our mind is that this graph is something m behavior like here, right? Then right now the time is that we want to find out the asymptotes. We have learned about asymptote is our supporting line to help us to draw the graph of the rational functions. So asymptote is actually a supporting line to help us to draw this particular graph is that we want to find out what is actually the horizontal or vertical asymptotes of the rational functions. So what is that? Right? We find the root. We find the hint from here, right? Isn't it? Because x cannot be 0,